Welcome back. Today we introduce a new tool in the study of the geometry of subsets of Euclidean spaces. Let's start with a Borel subset with finite HS measure, Hausdorff measure. Then, from this finiteness, it follows that the measure, which is restriction of HS to A, namely that measure of any set is given by HS of A intersection with U, is a Rodin measure on Rn. Our density condition, the upper density result that we had, can be read by saying that at almost every x, the measure of a ball centered at xr is bounded from above by a constant s power of r for every r positive. So this was basically our upper density bound. What this is saying is that a set with Hausdorff dimension S and finite HS measure cannot be too concentrated around neighborhoods of any single x. As our typical example goes, one example of a set with a point with infinite or very large density was multiple copies intersecting at that point, then we see that this neighborhood, the length of the set is way more than just one copy of r to power 1. And that result that we had is saying that this cannot happen pretty often. So this is a growth condition on how much of the set can be concentrated in a neighborhood of one single point x. A different way that people have found that describes this phenomenon is through the notion of density. So given some t positive, and so given this data and the Rodin measure the T energy of this measure is defined by the formula that you integrate the value 1 over x minus y length, just distance of x to y to power t, against the measure against the measure mu. So this is a double integral. To be really precise, this is an iterated integral. So you do one integral first and then you switch. This is a quantity in variable y and then you integrate again. So let's write it down. Is called the T energy of mu. Let's see what this quantity tries to capture. When does this quantity really blow up to infinity? That is when the values x and y are pretty close, so that the denominator is almost 0. Therefore, if for a significant set with big measure, so for some values of, so suppose we freeze x and then there is a subset very close, subset of y values, all very close to x, so that this quantity is really small for all those values of y, and they constitute a large measure. So for this quantity to be really big, for it to go to infinity, you want a lot of y values in a vicinity of x, and the measure of this red part is quite large. So y in red implies that x minus y is much small, but the measure of such y's is very large. So in this case, you would have this quantity going to infinity. So the largeness of T energy is a quantitative way to capture this idea of how much, in terms of measure, the set can be concentrated around a single value. Of course, by definition, it is what it is, and this is only heuristics, of course, exchanges and things like that. And there's, of course, this balancing out with this T and also the measure. It turns out that this quantity beautifully works hand in hand with the Hausdorff dimension of a set. So how do we relate this quantity to a set? It's through this set of Radan measures supported in the set, which we had seen previously in discussion of Frossman's lemma. So let's define MA to be the set of all Radan measures on Rn. So A is a subset of Rn, and we define this set of measures with compact support. So mu as compact support. Moreover, support of mu is contained in A. These are not equivalent or redundant because A itself could be non-compact. And finally, that the measure of the whole space of Rn is actually finite and positive. So some people may call these distribution of mass because by scaling, you can assume that the measure of Rn is 1, and then this is saying that that total measure of 1 has been distributed on parts of your space within a compact domain. Okay, so if I start with a set, then I have a collection of Radan measures with compact support, which are connected to the set A through this inclusion. So what is the upshot? What is the punchline? The punchline is that the dimension of Hausdorff measure of A will be computed by studying the values of T for which this energy is finite. The easier way to get there is actually through an intermediate definition. So the S capacity of a set A. So I will also talk about the terminology with capacity and energy and things like that. Okay, is, so let's write capacity, S capacity of the set A. What is that by definition? Okay, you look at 1 over the S energy, so it's just S replacing T from above. For these quantities, so you look at the largest such quantity that you can get by choosing measures from this set up here. And up to normalization, because otherwise you could just multiply mu by numbers. So of course such normalization is necessary for this to be well defined or not zero all the time. Okay, the convention is also that maybe there is no such measure with this property because we're just having any set and any S, so they're not necessarily at this point connected. So the convention is that if you cannot find such a measure, so that this is an empty set, then the supremum is assumed to be 0. Supremum of empty set being 0 is very consistent with many other definitions in geometric measure theory. I don't want to get into the tricky details, but it's often has to do with that something is, well, empty set means that you cannot do certain things with a set. It's either too huge or too small. Okay, and then okay. So here is the first result that we have relating now these notions. So fix a subset of Rn arbitrary. Then, so this is theorem 8.7 from Mattila's book. So if S is positive and Hs of A is finite. So this is actually just a redundant thing because we didn't consider counting measure for the whole course. So basically just saying that this is saying that the Hausdorff dimension of A is no more than S. Then the S capacity of A is 0. Okay, so if you the counterpositive would be that if you compute the S capacity and it was positive, so the equivalent would be if the S capacity of A was positive, then the S dimensional measure of A must have been infinite, so that the set is probably larger than being S dimensional. So positive capacity, big capacity, means a big set. Okay, for this second one, we need this notion of capacitary dimension. So dimension capacitary of A. There are several equivalent definitions. So this will be the supremum of T such that there exists some measure supported in A. So from this MA with T energy finite. Okay, so this goes back up here. So for any measure, Radan measure, probably compactly supported, we define the T energy. And then this MA for a set is the set of Radan measures that are supported in A and are positive and finite on all of our N. So we go over T capacities of all such measures. And the largest T, for which we still have a measure with finite energy, T energy, the largest such T is, by definition, the capacitor dimension of A. And it is true, this is another result before actually 8.7, is that this quantity is equal to supremum of S's, so that the S capacity of A is positive, which is also equal to the infimum. These should be familiar from definition of, I mean, they are analogous to what happened with Hausdorff dimension. There is this critical number under which you have infinite Hausdorff measure, above which you have zero Hausdorff measure. So this is saying that there is some threshold such that the S capacity of the set is positive before it and 0 after that. Okay, so all of this so far just definition. The last claim relating this capacitary dimension of A to Hausdorff dimension is that the Hausdorff dimension of A is always at least as big. So far, let's recap. For any Radan measure, we define the T energy. Given a set, we can associate to it a collection of Radan measures with the main restriction that their support is inside A. That is how they are related to the set at all. We define the S capacity of a set by inverse of S energy, and then taking supremum over such stuff. So the theorem is saying that, first of all, if you have finite Hausdorff measure, then your capacity is 0. And secondly, the capacitary dimension of A is no larger than the Hausdorff dimension of A. So all of these in Mattila come before Frostman's lemma, and their proofs are quite straightforward. No big machinery is used, just coverings and definitions of Hausdorff measure and of these objects. The big theorem, where we use Frostman's lemma in the proof, is that if, remember Frostman's lemma applied to Borel sets, if A is Borel, then the capacitary dimension of A is actually equal to the Hausdorff dimension of A, which is kind of proving a reverse to 1, that also if capacity is 0, then Hausdorff dimension will be 0 if you add any little bit to that constant S. So I'm not getting into the details anyway. So here the main point is that proof relies on Frostman's lemma. And existence of Frostman measures. So the inequality you can do without this, but if you want the equality, you need to apply Frostman's lemma, and that is one of the motivations for the study of Frostman's lemma. You may wonder now, what is the motivation for such a result? Obtaining the Hausdorff dimension of a set through energies and capacities, potential theoretic definitions of Radan measures. The answer is that the Hausdorff dimension of a set is just that, through definition, a very geometric abstract object. We don't have too many tools in our hand to compute Hausdorff dimension of arbitrary sets or even estimate them. With this definition, we know, now that we know it is equal to the capacitor dimension, potential theory comes in. We have integrals, double integrals, we have Fourier transform of measures, we have product measures, and many more tools at our disposal from analysis and potential theory in particular, that allow us to work with capacitor dimension. But then once we get some information about capacitor dimension, we obtain results about the Hausdorff dimension via this equivalency claim. And one major result where this technique has been applied is to Marstrand's projection theorems that say if you are in R2 and you have some set, for generic dimension that you pick, which you can parameterize through this one. So if you project orthogonally onto the set, you will see some shadow of the set, and this projection results claim upper and lower bounds for the Hausdorff dimension of the projection of sets. And using this T energies gives actually a quite elegant proof of this result. This wasn't the original proof of the projection results, and it came later once this connection was better understood and discovered, probably. Marstrand did proofs in 2-dimension by using different other methods. Also, Beskovich had done earlier results, again through very direct geometric approaches. But that is not the only application. Probably in future we will talk about other ways that this potential theory approach can help talk about geometry of sets. Until then, have a great one. Thank you for continuing to watch, and also thank you for many new people here who have subscribed. Finally, please spread the word, and take care.